In this video, we're going to consider the idea of a confidence interval for mu, and remember mu is the population mean. So typically what we would do is take a sample mean and use that as an estimate for the population mean. Much easier to collect data from a sample. So we say the average height of, the year 12s in this class was whatever, and therefore we assume that might be reasonable as the population mean for all year 12s. What about if, rather than simply using the value of x as just one point where we estimate, so here's our value of x bar, and we say, okay, that's our estimate for the population mean. What if instead of doing that, we actually chose to use an interval estimate with the value of x bar as the center of the interval? So it might look something like this, where we say, here's our calculated value of x bar for the sample. What if we use that to be the center of an interval where this is some lower bound, this is some upper bound, and so we're a bit more confident to say that the population mean lies between these two values than to say the population mean is kind of specifically that value of x bar. So that's the idea of a confidence interval. Such an interval would be a confidence interval for mu. So how might we go about thinking about and calculating that confidence interval? Well, we know that for any random variable x where n is greater than or equal to 30, whether or not it's normally distributed or not, that the mean of the sample means will be mu, and the standard deviation of x bar will be sigma over root n. Now, because x bar is normally distributed for n greater than or equal to 30, or approximately normally distributed, what that means is that we could actually sort of standardize any distribution of x bar. So we're saying x bar is a normal distribution. Well, let's convert it to a standard normal distribution where, remember, the center or the mean is 0 and our values are standard deviation. So this is our rule here or our result for turning a value of a normal variable into a value of the standard normal variable. And we're going to do it where that's the mean and that's the standard deviation. So what that does, like I say, is turn our distribution, our normal distribution x bar, into a standard normal distribution z. And then what we could do is say, well, for example, we know that in every standard normal distribution, 95% of the values of z lie between 1.96 standard deviations below and 1.96 standard deviations above the mean. Here it is sort of graphically. There's our distribution of z with 0 as the mean. We know that 95% of the data lies between negative 1.96 and positive 1.96. So, substituting in our value for z in terms of, x bar and mu and sigma. We're just substituting that in there for z. So we're saying if there's 95% of the values lying between negative 1.96 and positive 1.96, then by rearranging that, we can actually turn that into a sort of interval for mu. So we can say, therefore, there's a 95% probability of mu lying between this value and this value. And generally that comes just from, if you take sort of 1/2 of the inequality here and rearrange this to make mu the subject, then you will get this expression here. And if you take the other half of this inequality and rearrange it to make mu the subject, then you'll get this expression here. So what we have now is an expression which says that there's a 95% probability that the population mean will lie between this value and this value here. And these are now involving x and, x bar and sigma in this case. We'll sort of extend that a little bit in a moment. So there it is, a 95% confidence interval for the value of the population mean is this as the lower boundary, so that's our L value, and this as the upper boundaries. That's our kind of U value there. So notice when we write out the confidence interval, we just write it like a set of, like an ordered pair, where the first value is the lower bound and the second value is the upper bound. We don't bother with this, inequality in here and the probability and that statement on the end. We understand that that's what a 95% confidence interval means. Now, if you think about it, so we're sort of saying x bar is the center of this interval, isn't it? Because it's x bar minus something and x bar plus the same thing. So x bar, our value that we calculated for the sample mean, is the center of that interval, and we're kind of getting a margin of error below and above. And what we're saying is that if we did this, 100 times, so we calculated the sample mean 100 times and did a confidence interval for all of those 100 values of x bar, then 95% of the time we'd expect that the real population mean lies in that interval that we've generated. Alright. Okay, now we can extend that a little bit further because it's not always a 95% confidence interval. We can do it for any z-score, and it generalizes to this here, where we just put z there as the z-score associated with that confidence interval. So 1.96 is the z-score associated with a 95% area. Now that is on your formula sheet. That is the formula for a confidence interval. Here's some, I should say that's got an S there rather than a sigma. So it's perfectly acceptable to use S as a reasonable approximation for sigma when we don't know sigma. Obviously, if we know sigma, we can use that. Here's some common ones. So for 90% confidence interval, Z's 1.64. Now that these aren't on your formula sheet, so you can either learn them or you can calculate them using inverse norm. Now, I'm not sure if you sort of remember how to do that. So if you go into inverse norm, and in your inverse norm, in fact, if we go through the menu, let's go through the menu and go, where are we? Stat, distributions, inverse normal. And so the first thing we want is an area. Now, can I just clarify here? If we're trying to work out a 90% confidence interval, that means 90% of the data, or 0.9 area, is in there. Now for an inverse norm, it's going to calculate all the area up to a particular point. So if we're going for this value of k here, then the area in there is going to be 0.05. It's going to be 5%, isn't it? If we're going for this upper value, then it's going to be everything up to there, which is going to be 0.95. So you can either calculate the sort of negative side or the positive side, but you need to remember it's everything up to that point. So if I said here 0.95, I'm not calculating a z-score for a 95% confidence interval. I'm doing it for a 90% confidence interval. So there it is, 1.64. Okay, so that is pretty much it. We'll do an example, but there was just one other thing I mentioned up there which I should say here, and that is the idea of a margin of error. And the margin of error is just this thing here, the thing that we're adding to get the upper bound and subtracting from x bar to get the lower bound. So margin of error, we could say, is just that z times s over root n is the margin of error. So there's, let me put a box around that. That one's not on your formula sheet. Okay, well, it kind of is because it's just that value there, isn't it? Alright, let's consider an example. So here we are, question 1 from exercise 15F. We're told that a university lecturer selects a sample of 40 of her first year students to determine how many hours per week they spend on study outside of class time. She finds that their average study time is 7.4 hours. if the standard deviation of study time sigma is known to be 1.8 hours, find a 95% confidence interval for the mean study time for the population of first-year students. So what she's saying here is the average of the 40 that she sampled was 7.4. She wants to know with kind of 95% confidence what that might mean the mean is for the entire population. So let's write down the information that we're given. Firstly, we're given that the sample size is equal to 40. We're also given that the sample mean is, what was it, 7.4 hours. We are given sigma in this case, so we can use that instead of the sample mean. So that was 1.8 hours. And we want our confidence interval to be 95%. So that means Z is going to be equal to 1.96. Now you might just start remembering these sort of if you use them often enough. We could now, using the formula off our formula sheet, we could grab our calculator and sort of work out the lower and upper bound. But since we're using our calculator anyway, it will actually calculate confidence intervals for us. So let's go across to our graphics calculator. Let me see if I can remember how to do this. So we're in statistics. We're going confidence. Oh, there it is. Confidence intervals down there. And we want a Z interval. Okay, now we can do it two ways. We can either have the raw data from the sample, or we can have the statistics. And in our case, we don't have the raw values from the sample, so we're going to use stats. We're going to put in our sigma value, which was 1.8. Our x bar, the mean sample, the mean of the sample was 7.4. And there were 40 students, and we want our confidence level. By default, your calculator will have it at 0.95, which is what we want for this one here. So there it is, the C lower and the C upper. And what we should notice is that X bar, the value of the sample mean, is smack bang in the middle of those. So whatever we subtract to get that value from 7.4 is the same thing we'd add to 7.4 to get the upper bound. So this is what I would put down as my syntax. So let me go across here and say Z interval, and the first thing on there, the Z interval, was our standard deviation and then mean, so 1.8, 7.4, and then the other two things were N and the confidence level, which was 0.95, and from that it returned a confidence interval. Let's go back and check. So lower, I'll go to 2 decimal places, 6.84, and upper was 7.96. 7.96. Alright, so that's our confidence interval there, and done pretty easily using our GDC.